Hello everyone, my name is Wei Pind, and today I would like to give you a presentation on the analysis of pinmilling of pharmaceutical materials by discrete element method. Without any further ado, I would like to start this presentation by giving you some background of milling. As some of you may know, the milling performance of particulates is dictated by the mechanical properties of the material and the operating conditions of the chosen mill, such as the geometry, process conditions, input energy, etc. Amongst all the different types of mills available in the market, pin mill stands out due to its small footprint, ability to mill dry, moist, or slurry materials, as well as its relatively reasonable energy consumption. Despite being proven to be quite an effective milling device, what happens inside a pin mill is not exactly known. The determinations of its performance is currently carried out by trial and error method. A thorough investigations of the particle dynamics inside a pin mill is hence very much needed to better understand the breakage mechanism inside the pin mill. In this work, we are simulating a commercially available pin mill, the Picoplex of Hosokawa Micron. As can be seen in the photos to the left, the Picoplex pin mill consists of two separate parts. One of them is stationary, where it has two sets of pins, while the other one is rotating, and it has three sets of pins. It has a rotor diameter of 40 mm and can go up to 60,000 RPM. As I mentioned earlier, what happens inside a pin mill remains a puzzle, as it is almost impossible to see through the device experimentally. In order to do that, we need to employ some sort of numerical tool to help us achieve that. We adopted discrete element method in our work for the investigation of the dynamics of particles inside the Picoplex pin mill. DEM is a very common tool used for solving the motions and effect of a large number of particles. It was originally limited to spheres only due to the limitations of computational power. But as the computers are getting more and more powerful today, modeling faceted particles is now possible. Rocky DEM is one of the few software packages that could simulate the interaction of polyhedral particles, and we use it to simulate the interaction of paracetamol crystal in the Picoplex pin mill. The video on the right gives you the preview of how the simulation looks like using this tool. Now, for those who are familiar with DEM, these are the input parameters that I use for this work. The parameters used are approximated from stainless steel and paracetamol. One thing I need to mention here is that the Young modulus of the particles is reduced to speed up the simulation. As we are not simulating a cohesive system, this should not affect the investigations of particle dynamics in the Picoplex. I should also mention that particle breakage is not simulated in this work, even though the software package is capable of doing so. Now, let's look at the variables that we study in this work. Using DEM, we investigated the effect of particle size, rotational speed of the mill on the particle dynamics inside the mill. Three different sized particles were used in the simulation. They each correspond to the British Standard Sieve codes of 300 to 355, 355 to 425, and 425 to 500 micron. In terms of the rotational speed, 4 different speeds ranging from 3,000 and up to 30,000 RPM were used in this work. By using DEM, we now have a way to actually see through the device and look at what happens inside the Picoplex pin mill. We can even track the trajectory of each individual particle. Here is an example of the lifetime of a paracetamol particles in the pin mill. We can see that the particle actually undergoes accelerations and decelerations through a series of collisions with both the stationary and rotating pins before it leaves the mill. Particle hitting a rotating ring in opposing direction can result in either accelerations or decelerations of particles. A rotating pin hitting a particle in the same direction will result in an acceleration of the particles. Before I move on to discussing the results, let's take a look at the velocity of the rotating rings. As I mentioned earlier, we have three sets of rotating rings. To avoid confusion, I will refer to them as inner, middle, and outer rings from now on. Even though they are all operated at the same RPM, the actual linear speed is different. The larger the diameter of the ring, the higher the linear speed. And of course, the linear speed increases with the rotational speed. The table shown here gives us a reference of the corresponding linear speed, depending on the rotational speed and the position of the ring. So this is the collision data tracked and recorded for each particles in the mill. On the y-axis, we have the average number of collisions per particle before they leave the mill. We can see that the highest number of collisions are against the inner rotating ring. Also, as we increase the rotational speed, the number of collisions increases as well, which makes sense as the probability of particles getting hit by the rings increases. What we are seeing now is a plot that shows the collision energy spent on each rotating ring. This is extracted from a simulation case of 327 micron particles being fed at 0.2 gram per second at 3000 RPM. We can see that the highest collision energy recorded at each ring agrees very well with their corresponding linear speed. Larger ring has higher collisional energy. What's interesting is that the total energy spent on the outer ring is not the highest, but instead the middle ring. This is a bit unexpected, but nevertheless a very interesting observation. Even though particle breakage is not simulated in this work, we could still, in a way, use some mechanistic breakage model to infer it. The plot you see in this slide is extracted from the work of Dogbay, where he investigated the breakage tendency of paracetamol using the impact breakage model of Guthrie and Jones. R star on the y-axis is the fractional mass loss of particles, and it is a function of particle density, size, and impact velocity. The slope of the line is a lump parameters of alpha h over kc squared, known as the breakability index. What we are after in this plot is the x-intercept, as this indicates the transition point from no breakage to particle chipping. Knowing this transition value, and with given particle size, we could then obtain the transition velocity for particle breakage of a specific size of interest. Combining the experimental data with the collisional data extracted from the numerical tool DEM, we could then infer the breakage tendency of the particle of interest under different operating conditions. The plot shown here is the energy spectrum of 327 micron particles being fed at 0.2 gram per second at different rotational speed of 3000 to 30,000 RPM. The dotted vertical lines represent the maximum collisional energy calculated from the outer rotating ring at different RPM. We can see that all of the energy spectra agrees quite well with the maximum collisional energy at a given RPM, but there still exists small portions of the collision that exceed that limit. This is an indication that the impact velocities of the particles are actually higher than the maximum linear speed of the rotating rings. The solid vertical line is the minimum energy or minimum breakage energy that we calculated from Guthrie and Young's model. We could infer from this plot that at 3000 RPM, 327 micron particles being fed at 0.2 gram per second will result in almost no breakage at all, as its collisional energy distribution is well below the minimum breakage energy required for breakage. At 6,000, 10,000, and 30,000 RPM, particle breakage will occur, but to a different extent. So remember, we discussed about the collisional energy being higher than the maximum collisional energy calculated from the outer rotating rings. So this is a plot of the impact velocity of particles against the inner ring at 3000 rpm. We know that the linear speed of the inner rings is 3.1 meter per second, but this plot is showing that the impact velocities of particles could actually go beyond that. A lot of times during the design of milling operations, the linear speed of the rotating rings is used as a reference, but that might not always be accurate, so that is something to take note of. And similar results have also been reported in the work of Bonagna et al., and the reference is given below. There's also another very strange phenomenon we observe for particles with bigger size. Here's an example. In this plot, we have the energy spectrum of 461 micron particles in the picoplex pinwheel rotating at 3000 rpm. We can see that the collisional energy recorded is way above the reference maximum energy for 3000 rpm. In fact, it goes beyond the reference maximum energy for 30,000 rpm. A thorough investigation reveals that what we see here is not due to the impact velocity of the particles being much higher than the expected value, but rather a direct result of particles getting nipped between two consecutive rings. As you can see from this image, the particles in red are actually getting nipped by the two consecutive rings, and hence causes really high energy being recorded by the DEM software. In reality, this particle would break. Though it has not been reported in pin milling, particle nipping in small clearance is actually very common in agitated powder bed with an impeller. Substantial shear stressing due to nipping could occur when the clearance of particle diameter ratio is less than 2.5, and it was nicely summarized in the work of Crutchley and Bridgewater, as the reference given below. So what we see here is an interesting discovery, because we always thought that particles are being milled down as a result of repeating impact in the pinwheel, but actually it could also be due to particle nipping if the particle size is close to the size of the clearance between the ring. However, this phenomenon is not seen at high rotational speed. The fact that at high rotational speed such behavior is not seen could be attributed to particles getting quickly dispersed by the rotating rings. At low RPM, particles tend to accumulate between the inlet and the inner rings, causing them to pile up. That in turn increases the chance of particles getting nipped by the rings, giving rise to the unexpectedly high energy levels. Right, so just to quickly summarize our work here. So the particle dynamics in a rotating pinwheel was analyzed, and it was found that most particles collisions are against the inner rotating rings, which is running at a lower speed. Increasing the rotational speed increases the average number of particle impacts, while having the largest number of collisions per particles, the energy expended at the inner rotating ring is the lowest. The highest impact energy is recorded at the outer ring, but most of the energy is actually dissipated at the middle rotating rings. Particle energy spectrum method was used in conjunction with mechanistic impact breakage model of Guthrie and Jones to infer the breakage behavior in a pinwheel. Particle nipping was found for the large particle size. So the case here is 461 micron particles, and this is actually approaching the gap size between the rings that is approximately around 500 microns. And this behavior was not seen when the rotational speed was increased to 10,000 rpm or higher. So this will conclude my presentation today. Thank you very much for listening. And before I close this presentation, I would like to acknowledge Adobe for funding this project. And thank you very much. And I'm happy to take any questions that you have.